Welcome back today for another episode of Jetstreams and Rocket Dreams. Today, I want to take you back here. This is a pivotal moment in space history. This is kind of a mission that's somewhat related to this busy space week that we've had, and it was really a mission that swung from groundbreaking success to a life-threatening crisis in just a few seconds. So I want to take a walk down memory lane, talk about the story of Gemini 8. This is a mission that tested the very limits of human courage, technical prowess in a vast and unforgiving expanse of space. And let's dive into that Jetstreams and Rocket Dreams today. Let's go. All right, another episode here. My name's Tori from Overlook Horizon. Welcome back for Jetstreams and Rocket Dreams. Today, we'll take a deep dive into a Gemini 8 mission. This is one of the building blocks in human spaceflight here. It's a story that I kind of love, but also kind of terrifying at the time. And it really kind of goes to show like the things that we had to deal with as we were building the spaceflight program and having to take advantage of the technical knowledge and the bravery of some of those early astronauts that really were putting their lives in danger here. So this is Gemini 8. So let's kind of set the stage for what the Gemini program really was. So the Gemini program, this is NASA's intermediate step between Mercury and Apollo, right? Gemini aimed to develop essential techniques for the lunar missions. The program was going to introduce all sorts of critical advancements, right? Mercury got us into space. Apollo was going to put us on the moon. Gemini was going to develop these advancements like spacewalking, extended orbital flights. And one of the most important things was orbital rendezvous and docking, right? So if you can't rendezvous and dock, we're going to have a hard time landing on the moon, because if you forget, the lunar module undocked from the command module would go land on the moon. Then it would ascend from the surface of the moon and would have to rendezvous and dock with the command module again before returning back to Earth. So rendezvous and docking was kind of a big deal, something that we really had to perfect. And up until this point, nobody really was that confident that we could do it. And that's where the Gemini program came into play. So the Gemini spacecraft, we had tons of upgrades over the Mercury capsules, had much better onboard computers, much better maneuvering thrusters, and they could really do these kind of precise orbital adjustments and docking maneuvers that they were going to have to demonstrate. Now, they did try to do this before Gemini 8. They tried to do it with Gemini 6, but the Agena target vehicle actually exploded and had an anomaly during launch. And so they couldn't do it. So they did do kind of a rendezvous maneuver with Gemini 6A and Gemini 7, but they couldn't do what they had planned to do originally, and that's where Gemini 8 came in. So this mission was designed to achieve the first docking between two spacecraft. It was going to be the Gemini capsule and an unmanned Agena target vehicle. And this is going to be a critical milestone. They have to prove that the techniques that they wanted to use for their lunar missions later on were actually legitimate, and we're going to be able to do what they needed to do. Now, we had two astronauts on board. You've got Neil Armstrong. Everybody knows Neil Armstrong, obviously, these days. But before joining NASA, Neil Armstrong, he's an experienced test pilot, flown in the Korean War. He tested all sorts of cutting-edge aircraft at Edwards Air Force Base. And he was kind of known for having tons of skill and being cool under pressure. And this is kind of ideal for the challenges of space flights, this kind of unknown frontier that we're exploring. With him is David Scott. He was an MIT graduate, Air Force pilot. He had tons of technical knowledge, practical experience, and his skills were really suited for the complexities of orbital maneuvers and this docking maneuver that they were going to do. Now, leading up to the launch, Armstrong and Scott, they went through months and months of intensive training. They did countless hours in simulators that mimicked this docking procedure. They did also have emergency scenarios that they might face in orbit. And they're also building on some of the previous Gemini missions. They did have, as I mentioned, Gemini 6A and 7, which had successfully demonstrated rendezvous techniques. They came within one foot of each other. And really, Gemini 6A and Gemini 7 could have docked with each other, but they weren't really equipped to actually do a docking maneuver, because originally Gemini 6 was supposed to dock with an Agena target vehicle, just like this Gemini 8 mission. Instead, they just did a rendezvous and came really, really close. But this sets the stage and does kind of give a little bit of a building block for Gemini 8's attempt at docking. And if you think back on kind of the public and media engagement, back in the Apollo days, obviously it was huge. We're in the midst of the Cold War. We're all excited that we're trying to put astronauts in space and head to the moon potentially. So, this idea, all the Gemini missions really, but even this whole docking and rendezvous really captures the public's imagination, and we're kind of elevating expectations for Gemini 8. And the mission was seen as not just another test flight that was kind of meaningless. It was actually seen as a precursor to the moon landing. So very similar to how a lot of the public gets very excited about Starship these days, and how we're leading up towards lunar landings again, potentially missions to Mars. I mean, the public looked at the Gemini program like, all right, we're building what we need to go head to the moon someday. So really, a lot of people were interested in this mission. Now, the mission starts, this is March 16th, 1966. We get a launch from Complex 19 at Cape Kennedy Air Force Station at 11:41 in the morning. Spacecraft is carried into orbit by a Titan II GLV, and this is basically a modified intercontinental ballistic missile that was designed for crewed spaceflight for NASA, but it's really just an ICBM. And that's kind of how the early space days started. Neil Armstrong, David Scott, they're fully suited. They do all their checklists, and the ground crew actually notes and says that they seem very calm. They got a very calm demeanor, which is typical for a test pilot of those days. Like, this is kind of routine for them, and they're ready to go. Weather that day was almost perfect. Clear skies, mild temperatures. It's a perfect launch day for tracking, for recovery, for all of this. So everything's looking like it's going to be a great, fantastic day.
We have a mission. And we have a liftoff at 3 seconds. 3 seconds. Neil Armstrong reports the clock has started. Roll program is in, Armstrong says. 20 seconds into the flight.
They have a flawless launch. Gemini 8 goes into its initial Earth orbit. It's about 11 minutes after launch, and it's a nearly perfectly circular orbits, and all their parameters are in expected ranges, and they're pretty much ready for this rendezvous with the Agena target vehicle. And now the Agena, that launched 101 minutes before Gemini 8 from the same Air Force station.
T-minus 11, 10, 9, 8, 7, 6, 5, 4, 3. We have ignition.
There's ignition, and the Atlas rocket showers its pad with a bright burst of flames. It's airborne now, and it's rising into the sky, a beautiful liftoff. It's a smooth flight. Everything is going as it should be. You can now hear the thunder as it sweeps across our NBC observation point. Typical rattlesnakes and alligators out there are pretty good shaking, I would say. It's a smooth flight. She looks good.
And really, this process is not like today's International Space Station docking that has, now we can do automated dockings with computer-controlled systems. I mean, for the most part, this is absolute precision, control, calm under pressure for these astronauts to dock with this vehicle. So Neil Armstrong's carefully maneuvering the spacecraft to align with the Agena target vehicle, and it's got to be super, super precise.
This is Gemini Control Houston. About 2 minutes ago, Neil Armstrong called in over Tananarive, and he was able to confirm at that time that radar lock had been established.
Roger. Do you have solid radar lock on with the Agena? Over.
That's affirmative. We have solid radar lock. Just a second, I'll give you our current range.
Roger, thank you. Sounds good.
We're indicating 178 miles range and elevation of about 4 degrees.
The docking mechanism on Gemini 8 is a cone-shaped docking collar that's designed to fit into a drogue on the Agena target vehicle. And that makes sure that those two crafts can kind of latch together mechanically once contact is made.
Houston, this is Gemini 8. We're station keeping on the Agena at about 150 feet. Way to go, partner.
You done it, boy. You done a good job.
Do the thing.
Boy, look at that sucker.
That's beautiful. See the dipole?
Do I ever? I see everything with that fella.
Man, that's great.
Man, that is really slick.
A bit of all right.
Okay, the first thing we really have to do, platform parallelism, 650 to 710. And they're giving us the SPC loaded yaw maneuver. It looks like at nominal time. So they're going to give you that time. I'll check your whole status display for you. I bet those Lockheed guys are just jumping up and down.
The S10 is on.
Yeah.
Okay.
So it's about 6 hours and 33 minutes into the flight. Gemini 8 successfully docks with the Agena target vehicle. Neil Armstrong reports back to Mission Control. They say,
Flight, we are done.
and this marks the first time that two spacecraft had ever docked in orbit. This is a monumental achievement in space exploration. And initially, everything is stable. Mission Control is cheering. Everybody's celebrating. It's a fantastic day for space flights. They can't believe we finally done it. We finally docked two spacecraft together. And so initially, the astronauts do a couple of system checks, make sure all the connections are secure, spacecraft systems are functioning. The Agena target vehicle, I mean, it's not just a passive participant in this process, procedure here, is actually equipped to perform some propulsive maneuvers, which in future missions they could use to kind of adjust the orbit of a docked assembly. And that was critical to kind of demonstrate capabilities for lunar mission planning as well. And back on Earth, Mission Control celebrating. They all are excited about the success of docking. And the next thing that's going to happen is David Scott performs some maneuvers to test how the combined spacecraft now handles. What's the stability like? What's the control like? These are critical tests for validating that they know the handling characteristics of these two vehicles, right? So we've now got a much larger vehicle. It's got a different moment of inertia. It's going to maneuver a whole lot differently than if you're trying to maneuver just the Gemini spacecraft around. So they want to validate that what they think is going to happen is going to actually happen. The instruments on both the Gemini and the Agena, they're collecting data about this whole process, about the whole docking procedure, and they're making a few slight orbital adjustments to kind of position themselves for the next phase of the mission. You know, these adjustments are using the Agena's propulsion system, and they're getting this real-time data on how these maneuvers might be managed in longer, more complex missions. And initially, the astronauts report back and say that, well, the handling qualities here of the docked assembly are performing pretty much as they were expected. You know, they would report any unexpected behaviors or issues or things like that. But for the most part, everything is going pretty well. Nothing much to really be reported on. And then things change. We get about 27 minutes after the successful docking. Gemini 8's orbiting over the eastern coast of China. And Neil Armstrong and David Scott, all of a sudden they notice a slight yaw movement. They didn't initiate it. They're like, why are we moving? I didn't tell the spacecraft to move, but all of a sudden we've got a yaw movement going on. And initially, it's pretty subtle. But pretty soon it starts to escalate and kind of signals that, all right, we might have a problem here. And that yaw movement quickly turns into a roll. And then the spacecraft begins pitching, and the rate of spin starts to increase dramatically. And at one point, it's reaching up to about 1 rotation per second. And now they're really into a problem here. The rate of spinning here is becoming disorienting, and now it's posing a risk to the astronauts' safety, right? This is not just a spinning spacecraft out in orbit. Now we got the problem where if it spins too fast, like our astronauts, they might pass out. And, these are the early days of spaceflight. We kind of need those astronauts to fly the spacecraft. So initially, they're starting to, I wouldn't say panic. Panic is not the right word, but they're trying to figure this out in a hurry, right? Armstrong and David Scott, they initially kind of think that the problem might be with the Agena target vehicle. They think that the Agena might be causing this uncontrolled movement. And so they're thinking, all right, you know what? We got to undock. Let's undock, and then we'll solve the problem. But after a few minutes, they're checking their systems, and they quickly realize that the issue is actually not with the Agena, but it's with their own spacecraft. It's with the Gemini spacecraft. Specifically, it's one of Gemini 8's Orbit Attitude and Maneuvering System, or OAMS, OAMS, thrusters. Specifically, number 8 was stuck in the open position, and that was causing this uncontrollable spinning and rolling. Now, they're trying to communicate this kind of growing crisis back to the ground, and, communicating with mission control is kind of critical. You got a lot more people on the ground that can help troubleshoot this sort of thing, but they're also spinning rapidly, and that's making communication with the ground really difficult. So that's adding to the challenge here. They can't get firm communications with the ground. They're getting some things out to the ground. It's not too terrible, but this is also early days of space flight, so communications weren't really that spectacular to begin with, and now we're spinning and rolling, and communications are pretty tough. So spinning is getting worse and worse by the second, and Neil Armstrong makes really a critical decision to undock from the Agena. He's hoping that he undocks from the Agena, and maybe that'll stop the spin. This is kind of a risky maneuver, to be honest, because right now, while you're docked with the Agena, you kind of can feel the progression, right? So you inherently feel the trends of what the vehicle is doing and kind of where this problem is heading. But if you undock from this Agena target vehicle, all of a sudden that can change the characteristics of the problem, especially once your vehicle changes size and moment of inertia changes, and you could have a whole different issue here. But Neil Armstrong feels like this is necessary so that they can isolate the problem to just their spacecraft. But what happens is immediately following the undocking is actually the spin gets worse. It intensifies.
We got serious problems here with the coupling end over end, but we're disengaged from the Agena. Okay, we got your spacecraft 3 indication here. We're showing you spacecraft 3. What seems to be the problem? They're rolling up and we can't turn anything off. Signaling increasing in a left roll. Roger.
CSQ flight.
Go ahead, Blaine.
Did he say he could not turn the Agena off?
No, he says he is separated from the Agena and he's in a roll and he can't stop it. His rate pressure is down to 0, his ohms rate helium pressure. Gemini 8 CSQ. Stand
And now we're really putting immense physical strain on both the astronauts, and this is kind of increasing this sense of urgency that, hey, we really gotta sort this out here. We're really running into a problem. So, recognizing the severity of this problem here, Neil Armstrong decides he's going to shut down the malfunctioning OAMS thruster, and he's going to activate the Reentry Control System, or RCS. And this is normally reserved for controlling the spacecraft's orientation during reentry as they're coming back to Earth. But he decides he's going to try to use the RCS to kind of regain control of the spacecraft. And so he activates the RCS, uses the thrusters, counteract the spin. This is a critical, crucial, and effective decision because it actually does kind of stabilize the spin. But now he's used a significant amount of that RCS fuel, which was pretty limited, and they need that to come back to Earth safely. So it was a pretty tense couple of moments there, but they are able to get it back under control, and now they've got a couple more critical decisions to make. So the spacecraft has stopped spinning, they've regained control, but now they realize that they've used way too much of their RCS fuel, and that's a pretty limited resource. So what are they going to do at this point? So now they're communicating with Mission Control about their fuel status, letting them know what their readings are, overall condition of the spacecraft. Remember, the astronauts are kind of the eyes and ears on board there. So they communicate all that back down to Mission Control, and it's decided that given the potentially dangerous shortage that we now have of RCS fuel, and they really don't know if the OAMS thrusters can be reactivated or relied on at all at this point, they decide they're going to abort the mission. This is going to prioritize safety of the crew. They say, you know what, we're going to forget the rest of the mission objectives. Let's just abort, and we're going to come back. So now they got to plan re-entry, right? You can't just abort immediately and come back. You don't know where you're going to land, so you got to kind of have to plan for this re-entry. And they got to determine the optimal time, the orientation for the re-entry burn, and prepare for this kind of emergency splashdown in the Pacific Ocean. And not only that, they got to make sure there's recovery crews that are there. They got to communicate with the recovery crews. The recovery crew is going to be a U.S. Navy ship. Specifically, it's the USS Leonard F. Mason. That's the ship that was tasked with recovering them after splashdown. And so the astronauts are going to get themselves ready for this emergency splashdown procedure that includes things like they're going to secure all the loose objects that are in the spacecraft. They're going to check their harnesses, make sure that all their communication systems are working with not only mission control, but they also have to be able to communicate with those recovery forces in the Pacific Ocean. And so it comes time. They're going to initiate their re-entry burn. They have to use pretty much the rest of their remaining RCS fuel to do that re-entry burn. And this has to be executed precisely, again, because they're already critically low on RCS fuel. So they're going to use that, do the re-entry burn, and enter the atmosphere, make sure they're coming in at the correct angle. They don't want to overheat. They don't want to skip or bounce off the atmosphere and head back out into space. That would be a huge problem. And so they also, typically need those RCS thrusters for that whole orientation process during re-entry. And so re-entry is kind of a pretty tense time as they're monitoring spacecraft's angle, the heat shield integrity, what their heat temperatures are, their speeds. They got high speeds and heating during re-entry, like we just saw with that Starship flight that just happened a couple of days ago. And so after a pretty tense re-entry, they are successful. They're able to maintain control. They manually adjust the spacecraft's orientation when they need to manage the heat dissipation and distribution across the vehicle, control their descent speed. And Gemini 8 finally splashes down in the Pacific Ocean. They're about 500 miles east of Okinawa, Japan. And it's only 10 hours and 41 minutes after launch. USS Leonard F. Mason, they quickly find the crew. They go pick them up, recover the capsule and the astronauts, and make sure that everybody's safe now that we've kind of abruptly ended this particular mission. But now starts the whole process of kind of analyzing what happened, what went wrong. And that's where I think it's really relatable to today when you look at, things that have gone wrong with Starship or the thruster trouble that Starliner is having right now. Like, a lot of those are not as big of a deal today because we're building on lessons from missions like this that happened so long ago. So, following this safe recovery of the 2 astronauts, NASA is going to initiate this huge investigation to pinpoint and figure out what the cause is for this thruster malfunction that happened. And they quickly identified that thruster number 8 had been stuck in the open position. It's likely due to an electrical short within the thruster's circuitry. And that's what caused the uncontrolled spinning and jeopardized the astronauts, the whole mission, the whole thing here. So in response to that, engineers at NASA, they revise the electrical system, thruster designs for future Gemini missions, and they're going to enhance the isolation of electrical systems. They need to improve redundancy to prevent similar issues, right? We talked with Starliner with this helium leak that they launched with, but they also have, not only did they launch with the helium leak, but there were layers there where they've got 2 or 3 or 4 sets of redundancies that they can deal with that. Maybe back in the Gemini days, we didn't have a ton of redundancies, right? We lost our main OAMS thrusters. They did have the option to use those RCS thrusters, but really those RCS thrusters were planned for reentry, so they couldn't use them a ton. Fortunately, it works out in this particular scenario, in this mission. And this also changes the way that they train astronauts for future missions. Because Gemini 8 leads to changes in astronaut training. They're going to emphasize that astronauts need to be able to handle unexpected situations, equipment failures in space. Simulators get updated to make sure there's more failure scenarios and improve on astronauts' readiness to respond immediately to a hardware failure or something that's unexpected. And one of the interesting things that I think at the time, right, we look at the environment today, and we see things like the helium leak and the public response to that for Boeing Starliner, and it's a little bit different than it was then. Granted, like now we have Boeing Starliner and SpaceX, so there's kind of this little competitive feeling these days. But back then, right, Gemini was like the United States spacecraft. It was for everybody in the United States. That was representing everybody. And what happens is, Gemini 8 has this critical problem, dangerous to the astronauts, could have gone a whole different direction and put people's lives at risk. People's lives were at risk, but it works out okay in the end. And the mission finishes, but the public reaction is not that NASA's a failure. The overwhelming public reaction at the time was actually that it almost reinforces confidence in NASA's ability to manage crisis in orbit during human spaceflight. And that is something that I do find interesting, because instead of looking at it like, oh, NASA's a failure, we should just give up, right? We looked at it at the time. I say we like I'm talking for the general public, but they looked at it at the time like, hey, you know what? Things went wrong, but NASA did a great job of handling it. And they were able to handle crisis, and humans were safe. And they didn't really look at it like a failure. They almost looked at it like a success for NASA being able to handle crisis, knowing that things might go wrong in space flights, but they were actually able to bring the astronauts home safely. Fast forward a couple of years to something like Apollo 13, and this sort of thing comes back again too. But I do find it pretty interesting that the public reaction at the time, how people were kind of empowered by that, the ability to bring home astronauts safely after a problem in flight. So one of the other things that happens here is they do recognize that effective communication during spaceflight missions is pretty critical. as well. So they do make upgrades to communication protocols. Technology upgrades are being made to make sure that future missions can really be in communication with the ground because of how fast something like this can turn from a happy, successful day in celebration to all of a sudden our astronauts' lives are at risk. And this also leads to a review of mission objectives and priorities. They conducted a pretty comprehensive review of the mission planning and management process to lead to a little more flexible mission planning in the future and allow for adjustments in real-time conditions to almost plan for the unexpected. So it does end up having a lot of positives in the end. You know, they do still dock, and they have a successful docking. They're able to demonstrate a lot on this particular mission. And they're collecting data, but it's almost a whole second objective that they really didn't expect to have, which was how to handle this crisis in space. And that almost turns into the bigger success of the entire mission, is how to handle crisis in space. And that really goes forward into all the future spaceflight missions after that because of this, what could have been deemed as a failure at the time, but is deemed a successful failure. I know that term is used for Apollo 13 a lot, but it's almost deemed a successful failure because of how well things worked out in the end. And again, they still achieve this monumental milestone of docking, rendezvous and docking. Rendezvous we'd already done with Gemini 6A and Gemini 7, but now we've officially docked with another vehicle in space, and that is super critical. And now Neil Armstrong, David Scott, they're both looked at as kind of heroes, being calm and effective and calm and cool under pressure. You know, they're really lifted up on a pedestal after this kind of mission and be able to bring it home safely. And a lot of these changes get implemented going forward, and we're now in a much better place to handle crisis in space thanks to a problem like this. And this is why I kind of wanted to bring a story like this up and kind of revisit this, because it is easy for a lot of naysayers to look at problems that Boeing has had recently, or even problems that SpaceX has had developing Starship. A lot of them are very public and very open and easy to criticize and say, oh, it's such a failure. Look at this engine exploded during the landing burn. Look at the helium leak that Boeing is having. Look at the flap that was melting on Starship. Oh, they don't know what they're doing. They've failed. It's a disaster. But in each of those failures, we're really adding to the building blocks of spaceflight. And yes, sometimes space flights can be hard and lessons get learned more than once. Obviously, we'd love to see lessons only get learned once, but sometimes we learn part of a lesson and maybe not the whole lesson. But each one of these, I wouldn't even call them failures, but each one of these troubling issues or steps that they have to take to perfect the system, as long as now we know to kind of plan for the unexpected and we can prepare missions that are still safe and can handle anomalies going forward, and that perfection doesn't have to be the measure of success. We can still have a successful mission. We can still achieve objectives if we plan for them and we plan for these anomalies and we know how to handle these anomalies ahead of time as we get ready to put humans into space. And that's going to be something that Boeing still works on. We'll see how their landing goes coming up as the astronauts come back from the International Space Station. We'll see how Starship responds to, Starship's flight was nearly perfect, but not perfect, right? 2 engines failed, one during the ascent, one during the landing burn. Obviously, we've had the MVP flap that melted. They're going to have to sort that out, but this is how space flight works. This is how we build our way forward to a better program, and one that is robust and ready to fly humans. So I think that's where I'm going to end it here today. Appreciate you joining me on this particular episode. A little walk down memory lane. The Gemini 8 mission, huge success, but a brief moment of terror for some pretty brave astronauts that are, basically flying on a ballistic missile. Or at least that's how they were put into orbit. It's crazy. I don't know if I'm brave enough to do that myself, but I'm very grateful for those that came beforehand that were willing to sacrifice their lives potentially to improve spaceflight going forward. So, well, that's going to do it here for me. Thanks for joining me here on another episode of Jetstreams and Rocket Dreams. If you like this kind of stuff, definitely let me know in the comments. Let me know what other spaceflight stories or topics you want me to cover in the future. I might just cover your topic. Let me know in the comments, and we'll do another one of these in the future. All right, my name's Tori. This is Overlook Horizon. You're listening to Jetstreams and Rocket Dreams. Thanks for joining us, everybody. Have a good day. Goodbye.